let's integrate. Series and integrals are not entirely unrelated. Well, here I've got a graph, and I've drawn a bunch of boxes in red on my graph. Each of these boxes has width 1, and the heights of these boxes are given by the terms in a sequence. So the first box has height a sub 1, the next box has height a sub 2, the next box has height a sub 3, the next box has height a sub 4, and so on. Now, since the boxes each have width 1, it's easy to calculate their areas. The area of the first box is 1 times its height, which is a sub 1. So the area of the first box is a sub 1. The area of the second box is its width 1 times its height a sub 2. So the area of the next box is a sub 2. And so on. The area of the next box is a sub 3. The area of the next box is a sub 4. What if I want to calculate the area of all the red boxes? I imagine these red boxes go on forever. Well, that's really an infinite series, right? It's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and so on. So I could write the total area in all the red boxes as this infinite series. But there's more going on in this graph. I don't just have these boxes. I've also got this blue curve. That's the curve y equals f of x. And one special feature about this function f is that I've rigged it so that a sub n is f of n. And we can see that here because this blue curve passes through the corners of these boxes. Now, what if I wanted to calculate the area under the blue curve and to the right of the line x equals 1? Well, that would be this integral, the integral from 1 to infinity of f of x dx. How does this blue region compare to this red region? Well, this blue region sits inside all of the red boxes. Well, what does that mean? That means that this is the red region, this is this blue region, but this blue region sits inside all of the red boxes. And that means that the area of the red region must be larger than the area of the blue region. Why does that matter, though? Well, the takeaway message here is that this sum is even larger than this integral. And that means if I know that this integral, say, is infinity, if the area under the blue curve and to the right of the line x equals 1 is infinite, then what do I know about this series? Well, that series then must diverge. The picture includes some as of yet unspecified assumptions. So more precisely, I need to assume that f is a decreasing and positive function, and I should explicitly mention that a sub n is equal to f of n. And with those conditions, then if this integral diverges, then the sum also diverges. We're in a position to prove this. This is what I'd like to show. Suppose that little f is a decreasing but positive function. I'm building a sequence a sub n out of the function f. And I'm supposing that the integral of f of x dx, x goes from 1 to infinity, diverges. And I want to show that the series diverges as well. Well, to get a handle on this series, I'm going to look at this. The sum little n goes from 1 to big N of a sub n. And somehow I want to relate this sum to an integral. Well, I won't get there all at once, but I'll do it in steps. The first thing I can say is this, that the sum of the a sub n's is equal to the sum little n goes from 1 to big N of the integral x goes from n to n plus 1 of f of n dx. And although this looks somewhat fearsome, it's true for a not very deep reason. The upshot here is what? F of n is equal to a sub n, and consequently this is just the integral of a constant on an interval of length 1. So if you integrate a sub n, x goes from n to n plus 1, well, you're just getting a sub n. So this is the sum of a sub n, which is exactly what I've got here. But when I write it like this, I'm giving myself some more freedom to mess around with this integrand. Instead of saying f of x, I could say f of the floor of x. Well, why is that helpful? Well, what's floor of x, right? The floor of x is the greatest integer less than or equal to x. So if x is between n and n plus 1, and n's an integer, then the floor of x is just equal to n. And that means, except at the endpoints, f of the floor of x is equal to f of n on the interval between n and n plus 1. And that means this integral is just, again, a sub n. So the sum of the a sub n's is the sum of, well, this is just a sub n. Now I'm writing a sum of a bunch of integrals. All the integrands look the same, but the bounds of integration are changing, right? The first integral goes from 1 to 2, the next integral goes from 2 to 3, the next integral goes from 3 to 4, and so on. But if you add up a bunch of integrals, all of which lie end to end like that, you can just write that as a single integral. So this sum of integrals is equal to just the integral x goes from 1 to big N plus 1 of f of the floor of x dx. All right, so I've replaced this sum with this integral. Now what can I do? Well, I know that f is a decreasing function. So if I plug in a bigger input, the function's output is smaller. And that tells me that the integral of f of floor of x goes from 1 to big N plus 1, is bigger than or equal to the integral of just f of x goes from 1 to big N plus 1. Because f of the floor of x is at least as big as f of x. Now what else do I know? I know that this integral diverges, which means what? Well, it means that as long as n is big enough, I can make this as big as you'd like. All right, all you need to do is tell me how big you want this to be, and I'll tell you some big enough n so that this thing is really that large. But this thing is smaller than this sum. So what that means is that this sum can be made as big as you like, as long as you choose big N big enough. But if you can make this sum really, really large, that means the sequence of partial sums isn't getting close to any finite value. And what that means is that this series diverges. We can go the other way too. We can integrate to prove convergence. So again, I've got this integral and this series, and I somehow want to relate them. Well, let's suppose that this integral is finite. Then I'd like to be able to conclude that this series converges. Well, all the same conditions as before, right? I want f to be a positive decreasing function and such. Let's prove it. So here's what I've got. I've got that this integral is finite, converges. Then I want to know that the series converges as well. So here's the integral from 1 to infinity of f of x dx. How does that integral compare to just the integral from 1 to big N of f of x dx? Well, f's a positive function. So these things differ by the integral from n to infinity, which is some positive number. So this thing here is definitely an overestimate of this thing. So the integral from 1 to infinity is bigger than the integral from 1 to big N of f of x dx. Now I'm going to relate that integral to this integral, the integral from 1 to big N of f of the ceiling of x. Now remember what the ceiling is. The ceiling is the smallest integer bigger than or equal to x. So how does f of x relate to f of the ceiling of x? Well, the ceiling of x is always at least as big as x. But because f is decreasing, f sends bigger inputs to smaller outputs. So f of the ceiling of x is less than or equal to f of x. And that means this integral is an overestimate of this integral. Now I can split this integral up. Instead of integrating from 1 to big N all in one fell swoop, I can instead integrate like this. I can integrate from little n to little n plus 1 and add up all those integrals as n goes from 1 to big N minus 1. But on each of these intervals, I know exactly what the ceiling of x is. If x is between little n and little n plus 1, then the ceiling of x is just n plus 1. So now I've got the sum of the integral of f of n plus 1, but what's f of n plus 1? Remember, f of n plus 1 is just a sub n plus 1, and I'm integrating this constant over an interval of length 1, so this integral just ends up being a sub n plus 1, and that means these are equal. Now I could reindex this. The first term that I'm adding here, the n equals 1 term, is a sub 2, the next term is a sub 3, and eventually I plug in little n equals big N minus 1, which gives me a sub big N here. So I could instead write that as just the sum little n equals 2 to big N of a sub n. So altogether, right, what I've shown is that this integral, which has some finite value, is an overestimate of this, which is almost the partial sum. It's just missing a sub 1. But what that means is that the sequence of partial sums for this series is bounded. And I already know that it's monotone because all the things that I'm adding up are positive. So I've got a sequence which is bounded and monotone, and therefore, by the monotone convergence theorem, this sequence of partial sums converges, which is exactly what it means to say that this series converges. We're doing more than just proving convergence. What I mean is that I've got this inequality here. The big deal here is that I could add a sub 1 to both sides. And if I add a sub 1 to both sides, now I've got this inequality. But this is just a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub big N, which I already know is at least as large as the integral from 1 to big N plus 1 of f of x dx. So now take a look at this. I could now take a limit as big N approaches infinity, and here I would be getting what? Well, this would just become the series, the sum of all the a sub n's, and this is now the integral from 1 to infinity of f of x dx. So what I really know is that the value of this series is trapped between this integral and the same integral plus the first term. Let me summarize what we have. Same setup as always. I'm supposing I've got some function little f which is decreasing but positive, and I built my sequence out of that function. Then if I've got that this integral converges, if that integral has a finite value, that happens if and only if this series converges. Right? Because we've shown both directions. I've shown that if this integral diverges, then this series diverges, but I've also shown that if this integral has a finite value, then the sequence of partial sums here is monotone and bounded, therefore this series converges. And more than that, I've also got these bounds. I also know that the value of this sequence is trapped between these two values.